Alright, good afternoon calculus class today. So it's Mr. Chen. So yeah, it's me again. So this one is for sections 2.2, the limit of a function. So let's talk about the definition of a limit in calculus. So here's the one. So the limit of f of x as x approaches a, so equals L. So the way to express this one is showing that limit LIM, so we just abbreviate it, of f of x. So as x approaches a, so x goes to a. So this whole thing, so that equals L. L stands for constant. Okay, so constant. We can say that's one of those real number. It's a real number. Okay. And now what about the definition of a left-hand limit of f of x? So let's say we have a graph, kind of like a volcano, okay? So kind of like a volcano here. So the left-hand limit of f of x as x approaches a from the left, it's equal to L. Okay, so instead of making the volcano, let's just connect this. I don't want to put in the vertical asymptote here. So let's just connect this. So let's just make a curve. Again, this one's just the y-axis. So let's say this one's connected, okay? Kind of like a random normal distribution for stat. Okay, so limit as x goes to a from the left, so that equals L. So let's say that a, so a, it's over here. So let's say that a equals 0. So as you can see that the limit approaching from the left, so the limit, so let's say, let me give the scale. So let's say this one is 1 and 2. So that means the limit here from the left, so that would be considered 2 for f of x. Again, the bell curve is f of x. And now what about the limit approaching from the right hand side? Limit x goes to a from the right, so that equals what? Also L. And as you can see that if the limit, well, if a goes to 0 from the right hand side, so x goes to a from the right hand side, well, a, I'm supposed to use 0 because the value of a is just a real number, which is 0. Okay, so from the right hand side, so this one for f of x, so the limit, it's also considered what? 2. So basically it's the same kind of definitions, but the things that I just want to change the direction. So the right hand limit of f of x as x approaches from the right, it's equals to L. Okay, so this one is just the mathematical expressions for calculus. So now why do we need to discuss about the left side limit, the right side limit? So let's go back to this one. In order to have a limit exists, so let's say that L exists as x approaches 0. So in order to have a limit at a exists. So what that implies, well, what we need to show is that the limit as x goes to a from the left, so the limit here, it must be the same as the limit as x approaches a from the right hand side. Now what happens if those two side limit, if they're not consistent, if they're not equal? If those two left limit and the right hand limit, they're not equal, so that means the limit at a does not exist. So in order to have a limit at x equals a exists, so that means the limit from both sides must be exactly the same. Okay, so now let's take a look at this one here. For the functions h whose graph is given, state the value of each quantity if it exists. If it does not exist, explain why. Okay, so now take a look at that. Limit x goes to 2. So here's 2. Well, you might be wondering there's a hole here. So according to the definitions, so the function is not defined at this position, but does the limit exists? Well, take a look at that. The limit approaching from the left, would that be the same as the limit approaching from the right? So let's say that limit as x goes to 2 from the left. So this one's getting closer and closer to this position here. It's almost 3. It's like 2.99999. And then the limit as x goes to 2 from the right. So this one is getting closer to 3.0001. So eventually the limit is going to be considered 3. Well, we do know that's a hole here, but somehow the limit exists. So we can say that the limit is considered 3. And the reason why that is because the limit from the left at 2 is the same as the limit as x approaches 2 from the right. Because one is considered 2.9999999, and the other one is about 3.0001. So therefore the limit, eventually, it's going to be 3. And now what about the limit as x approaches 0 from the left? X approaches 0 from the left. That means we're looking at the piecewise function with this graph right here. So the limit as x goes to 0 from the left, we're using the 1 approaching from the left, the first piecewise function. So that one, it's exactly at 1. And what about the limit as x approaches 0 from the right? So that means we're using the 1 approaching from the right here. So as you can see that this one is getting close to 0 or negative 1 down here because the scale is 1. Down here is negative 1. Now you might be wondering, what about the slope at 0? The slope at 0 does not exist. If there's a question like that without the minus plus, so let's say that the problem is asking about limit as x approaches 0 exactly for f of x. So the limit is considered d and e. Well, because the limit approaching from the left, it's 1. But the limit approaching from the right at 0, it's negative 1. And those two left side and the right side limit, they're not considered the equal limit. So that's why limit does not exist at 0. And now what about the limit at 8? So here's what? 1, 2, 3, 4, 5, 6, 7, 8. So you might be wondering what happened with this curve right here. This one is called oscillation. So oscillation, that means this one is like going up and down, non-stop. It's just going up and down repeatedly. So if you see anything like that, it shows like a different boundary. It shows the boundary from 3 to 6. So there's like an unstable boundary. Anytime they see that the unstable boundary for the oscillation, so that means the limit also consider d and e. D and e, that means the limit does not exist. Okay, so again, limit does not exist. It's just abbreviation. Okay, so now let's see what else that we have for the next slide. So this time we need to go backwards. So the limit, they're all given with each position. So once we define those limit on the graph, so we'll be able to connect those dots, or perhaps it might be open circle, closed circles, or it might be considered like oscillation. We'll find out. And then sketch the graph, okay? So first thing that we have, so this one's a minus. So limit as x approaches 0 from the left, f of x is 1. So that one right there. So let me set up the scale here first. So let's use each box as 1, okay? And then the y-axis, let's just customize it. Let's just make it wider. So let's say this one is 1. Down here, it's negative 1. So we go by 2 unit as 1 unit. So the scale for this one, so 2 for 1. Okay, so limit x goes to 0 from the left, it's 1. So it's up here. So the limit approaching from the left. So we put in the little arrow, so just the indicator. And now the limit as x approaches 0 from the right, it's negative 1. So it's down here, approaching from the right. And then the limit as x goes to 2 from the left, f of x is 0. So at 2, right here. So the limit, it's considered 0 from the left-hand side. So that means approaching from the left here. So that's 0. And then the limit as x goes to 2 from the right-hand side, that's 1. So we've got to be very careful. So we do have 2 different positions here. So 1 is 0 when x goes to 2 from the left. And then the other 1 when x goes to 2 from the right. So that's 1. So if you do have like a unstable boundary, so for the y value, so let's say that we can put in the unit circle. So one is approaching from the left, the other one is approaching from the right. You know what? This one is 1, so that should be up here. Otherwise, that would be considered 1/2. Okay, let me just redraw that. So this one, again, x goes to 2 from the left, so the limit here is 0. And then limit as x goes to 2 from the right, so that's 1. And the reason why they're considered open circle, because that it's an unstable boundary. And then for f of 2, it's 1. So now, if there's another defined situation for f of 2 is 1. So that means at this position here, so this one, instead of being the open circle, it's going to be considered a solid circle. Because that the point is defined here at 1. I mean at 2. So at x equals 2, so the position is defined. But down here on the bottom, that just you consider an open circle. And then f of 0, it's undefined. Okay, so that one is undefined, so that means for those two, they must be considered open circle. So eventually, once you connect the graph, so it's going to be like this. So one is coming from the left. It doesn't matter, it can be a straight line here, it can be a curve. And then the other one coming from the right, so this one got to be connected. So let's say like a line segment. And then the one coming from the right over here. Again, for the boundary, this one is continue. So it's all the way through. So again, this one could be a line segment, could be a curve, could be increasing curve, decreasing curve. This one too. But this one got to be connected because one is approaching from the left and the other one is approaching from the right. All right. So as what I mentioned before, definition of combination, left and the right side limit. So in order to have the limit at x equals a exists. So the only requirement, and that's the only requirement, so we need to satisfy that x goes to a from the left is the same as the limit as x goes to a from the right. So once both side limit consider the same limit, so that means the limit at x equals a exists. Evaluate the value of the limit if it exists by evaluating the function at the given number. So now this one, you don't want to plug in a number and try to do it individually because that would be kind of complicated. So the overall function is considered rational. And then the top part here, it's considered trinomial with exponential and linear. And down the bottom, we do have quadratic. So this one is the combination of all kind of function here. So what you need to do, you want to put it into the calculator. Now the reason why we cannot put in 0 because this one would be considered undefined. So we need to put in those number here. So let's set up the function first. So again, using the graphing calculator. Okay, so let me clear all this. So for y1, we do have a rational function. And according to the function, we do have quantity of e to the power of x minus 1 minus x. Okay, so the quantity, parentheses, so second, and then e to the power of x, bring it down, minus 1 minus x, minus 1 minus x, and then it's all over the quantity of, well, just x squared. So for that one, we don't need the parentheses, so just one term, so x squared. Again, we want to use the second table, so second graph or second table. Make sure that this one you can put in any random x value, so go to second table or second window here. Make sure that the independent variable got to be in ASMO here, and then dependent, it's automatic. Going back to second table. So now we can plug in those numbers. So according to the given value for x, we do have plus minus 1, plus minus 0.5, plus minus 0.1, plus minus 0.05, and then plus minus 0.01. Okay, so now let's put it in here. Second table. So let's start out with negative 1, so limit approaching from the left. Negative 1, and then negative 0.5. As you can see that the limit is getting close to 0.4 something. And now the next one, you want to put in negative let's see, back to the given value. So negative 1, negative 0.5, negative 0.1, negative 0.05, and negative 0.001, okay? From left to right. Okay, so negative 1, negative 0.5, negative 0.1, and then negative 0.05. As you guys can see that the limit is getting close to 0.49, or eventually the limit is going to be getting close to 0.5. And then the next one, negative 0.01. So this one just showing the limit approaching from the left hand side at 0. And now let's find out the limit approaching from the right hand side at 0. So let's say 1, 0.5, 0.1. Well, 0.1, we're going to do that later. The next one, 0.1 first. And then 0.05, getting smaller, getting close to 0. And then 0.01. And compare that the one with negative 0.01 and then 0.01. As you can see that the slope eventually is going to be getting close to 0.5 at 0. So therefore, what's the slope here? What's the limit? Not the slope. The limit when x goes to 0, the one approaching from the left and then the one approaching from the right, they're getting very close. And it's going to be at 0.5. Okay? So now let's see what else that we got for the rest of this. So this one's getting a little bit more complicated. Without using the calculator, how do you estimate the limit for the given rational expression? So we do have x plus 2 over x plus 3. So this one is a one-sided limit. So this one is showing that x is getting close to negative 3 from the left. So negative 3 from the left. So here's negative 3. So it's approaching from the left. It's a negative number. So that means consider negative 3.0001. So that means for the for x, the estimation, we want to use this negative 3.0001. So plugging a number, we do have negative 3.0001 plus 2 over, and then negative 3.0001 plus 3. Again, the decimal places, we can change that. We can expand it to even further. So the top part here, it's about negative 1 point something. So it's almost negative 1. So this one is just a random constant. But down the bottom here, this number is getting very small. It's negative 0.0001. It can be negative 0.000001. Keep going. So if you have a constant over a very small number, or very small decimal, hey, guess what? This one eventually is going to be getting to be a big number. Negative over negative, that's going to be positive. So eventually, this whole result is going to be considered positive infinity. Again, if you have 2 divided by 0.00000 blah 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 1, so eventually it's going to be like what? Like 2 million, 2 billion, something like that. So it's a very big number. And now let's do another one like this. So positive 5 from the left hand side. So 5 from the left hand side is coming this way. So that means this one we want to use things such as what? 4.9999. So let's say x is about 4.9999. So e to the power of 4.999 over 4.999 minus 5. Now for the top part right here, that's just a constant. But the denominator, what do you notice? So this one's getting close to be a negative very small decimals, like negative 0.0001 to the power of 3. So that means it's going to be another very small negative decimal. So a constant over a very small negative decimal. So eventually it's going to be considered negative infinity. So for the result here, So positive constant divided by very small negative numbers. Constant over a negative very small decimal. So that one is going to be considered negative infinity. So this one here, then that'll be considered negative infinity for the limit. And now what about this? This one is quite similar, but before you do that, you can always simplify it a little bit. So you might want to be thinking about like taking out the greatest common factor. And then the denominator, you want to factor it, x minus 2, x minus 2. Well, certainly you can do things like that. So this one got canceled, this one got canceled. So now we do have limit. X goes to 2 from the left. So it's x over x minus 2. So just make sure that's simply looking. So the top part here, that's it's 2 from the left. So 2 from the left, that's about what, 1.99999 or blah blah blah. And then the denominator is 1.9999 blah 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 minus 2. So again, as you can see that the top part is just a constant, it's almost getting close to 2. Constant. Minus, well, 1.99999 minus 2, it's like negative 0.00001. It can be, a very negative, very small negative number. So constant over a very small negative number, so that would be considered another negative infinity. And now what about for this? So x times cosecant of x. So another way that you can rewrite this one, it's like limit x goes to 2 pi from the left. If you're not quite sure what cosecant of x look like, you can always put in this one. Cosecant is written as 1 over sine of x. So this one is written as x over sine of x. Okay? So we do know that x goes to 2 pi from the left. So 2 pi from the left. So pi is 3.14 times 2, which is what, 6.28. So anything that's getting close to 6.28 from the left is like 6.2799999. And now what about sine of 2 pi? If you want to find out exactly what that is, well, sine of 2 pi, that would be 0. So for the sine curve, okay, let me just do it right here. Sine curve is just like a roller coaster. Okay, so actually started at 0. Okay, wait a minute. Something wrong here. Okay, so for sine of x, as you can see that here is what? 0. So this one's getting close to 0 from the left. So that would be considered negative 0.00001. So 6.2799999 constant over a very small negative number, 0.000001. Again, it's coming from the left. So again, once you divide it, what is that? It's a constant over a very small negative number. So eventually it's going to be negative infinity. So this one, what you need to do, you need to set up the boundary. So you want to find out any kind of estimation position for the x value or the y value. Well, but the thing is that it's all about the x value because you want to put it into the expression. So once you're being able to analyze it with a big number over a small number or a constant over a very small negative number, so then you'll get those unbound, which is the infinity or negative infinity. Alright, so now let's see what else that we have for the rest of this slide here. That's it. So again, so you're more than welcome to rewind or rewatch the video, especially the content like the last slide here, the one that's getting a little bit more difficult. So make sure that I spend some time to watch the analysis, the way that I explain it, and then try to do the practice. Alright, so I'll see you guys next time. Have a great one.